Shalom! It's been a long time since my last video. It's not like I haven't been working on anything. In fact, I've been quite busy with work. Even now I'm on a lunch break. But aside from driving a bus, I count maybe 6 videos that I'm currently working on. Here's a glimpse of one of them. It's nothing special really. Just rehashing my previous video with some improvements. Anyway, my channel is home to many emulator programming videos like NES and Microplays and DCPU16 and even PIC16. And people have been asking how to get started with emulator programming. And other people have been replying saying that Chip8 supposedly makes for an easy beginner's project. Up until people were talking about Chip8 on my channel, I had never heard about it. So I chose to study. I searched for Chip8. The Wikipedia article was the first match. So it's an interpreted programming language, not a real system, huh? Originally run on a system called Telmac 1800. What a lovely picture. So the limitations of this machine set up the limitations for Chip8 as well. Next I searched for documentation about the Chip8 architecture. And I found this page. Technically it seems I'm not going to write an emulator but an interpreter, because Chip8 is not a real system. Rather than duplicating what a real Chip8 machine does, I'm just creating a program according to specifications. And these specifications read as follows. The system has 4 kilobytes of RAM. The first half a kilobyte is reserved for the interpreter's internals. To be faithful to that design, I'm going to use the Union keyboard to overlap things like registers and keyboard arrays with the RAM accessible to the program. A cunning enough Chip8 program could even manipulate those variables directly. From the document we find there's supposed to be 16 base registers, 2 timer registers, an index register, an instruction pointer, a stack pointer and stack. And there's 16 buttons on the keyboard. The display is monochrome and has this small resolution. A small part of the memory is pre-initialized with a built-in font. Being fluent in hexadecimal number system is nearly mandatory when working on this kind of projects. Next we will get to my favorite part, the list of instructions. From the document we can glean that each instruction is 2 bytes long. Neat. This makes it super easy. Variable length instructions are not as nice to deal with. We also see that each instruction follows a command pattern. I'm going to copy this section of the document rather verbatim to my source code. Well, parts of it anyway. This is the complete list of instructions we are going to handle. I like to document my intent first and then worry about the implementation. So now I'm just listing the instructions in a manner as close to the original documentation as possible. Just so that I won't need the documentation page anytime soon, I'm also going to add the documentation into the source code, in a bit condensed format though. Many of these instructions contain references to particular registers. Why not pre-calculate those references, right? It will simplify the actual implementation of the instructions times 35. Instructions that do simple assignments and calculations are the easiest to do, so let's get them out of the way first. Then there are 6 instructions that skip the next instruction if a condition matches. Since each instruction is exactly 2 bytes long, skipping the instruction means incrementing PC by 2. Then let's do the arithmetic instructions that also change VF. The VF doubles as carry flag, an overflow flag and other such assorted purposes. While it is a full 8-bit register and can actually be used as such, these instructions only set it to either 0 or 1. Now don't tell anyone, but in this interpreter I'm actually slightly deviating from the document I'm supposedly reading. That's because I also read documentation from Wikipedia and other sources, and I found out that most modern Chip8 emulators do some instructions a bit differently than the original implementation on Telmac 1800 did. I'm following the original way. One such difference is that the stack is supposed to be 12 items long, not 16, and other is that the 2 last instructions in this list are supposed to increment I by the number of bytes read or written. In proper modern C++, generating pseudo-random numbers requires somewhat wordy syntax. I don't quite like it, but I do understand the rationale behind its design. The draw instruction is the most complicated one of them all. Although the what and why is perfectly documented, the how will have to remain as an exercise to the reader, as it's a bit difficult to explain. In any case, now that we have completely implemented all the instructions, all that remains is to decide which instruction to execute. There are many different ways to do it, some more efficient and some less efficient. Here I chose one of the less efficient ways that requires comparatively little code to write. For a system that only runs like 1,000 instructions per second, 1,000,000 times lower than a modern microprocessor, the difference in performance does not really matter at all. You also saw the gist of this design in my PIC emulator, although there I went a bit overboard with compile time calculation. Some people disapprove of using the preprocessor in C++ projects in the ways that I do, but for me it's just another tool, and I like to use it as that, a tool. Although I am a believer in the God of Abraham, Yitzhak and Yaakov, when it comes to programming I try to steer away from religiously held opinions. So now that the actual core of the emulator, interpreter, has been completed, that which is personally for me the most boring part still remains, the user interface. It consists of 3 parts: graphics output, keyboard input and sound output. I am using the simple direct media layer (SDL) library to provide these features. Should you wish to compile and run my interpreter, you will also need to download and install this cross-platform library. By the way, some people have complained that I type too quickly in these videos. I admit that I am a quick reader myself, and as such I tend to overestimate the speed that an average person reads, but I totally expect viewers to use the pause and rewind buttons when they need it. The completion of this project took about 2 weeks, by the way. I didn't do any bookkeeping, but maybe 3 days into the design and refinement of the emulator, 3 days into creating an assembler for the Chip8, 4 days into creating some sample Chip8 programs that you will see later in this video, and 3 days into recording and editing videos and sound. What you see here is obviously a simulated recreation of the completed interpreter, without any of the backhunting and redesigns over redesigns, because in my opinion, watching someone think, and there's a lot of thinking in programming, is not very interesting. Programming is not for the impatient man. Here we take a parting look at the beloved documentation to borrow just enough wisdom so that we might implement the timer registers correctly. The typical Chip8 implementation will run at an abysmal rate of some 20 or 50 instructions per frame, but I'm cranking that number up to 50,000 just because I can. If the Chip8 program can't handle that speed, it's badly designed. The system contains a timer register for timing purposes, and any game should use it. The system can also be halted completely waiting for an input key. Now for the final part to the interpreter. Sound support. Though my NES emulator did have sound support in it, its user interface complement of the sound support was seriously lacking. Not so in this emulator interpreter. Top-notch implementation there for those premium quality beeps. The Chip8 specification does not specify the kind of noise the system is to be making, other than that the sound is supposed to be contiguous and has 2 options, on and off. I managed to sneak a lambda function into this program at the final moments for just that purpose. It also just happens to be the most convenient solution. This is one of those parts that is kind of hard to explain. You need to understand how PCM sound works in order to understand this function. Luckily there's a great article in Wikipedia about that topic. Now I will compile the program and run it through a couple of demos I created. The first demo is a little Starfield animation. It runs until you press some key. The other one took significantly longer to create. It is the well-known puzzle game of Towers of Hanoi. There is a Wikipedia article of this topic game as well. The game objective is to move the disks from a pile to another pile, one disk at a time, without ever placing a large disk on top of a smaller disk. Once you succeed in the task, you will be given the standard game over screen and a report of how many moves you used. So anyway, that was Chip8. I hope this video was fun to watch and interesting and useful. Usually when I'm working on a big project for my channel, I try to release videos in the meantime that require less work to do. Some of my pending videos don't involve even programming or even technology. So thanks for watching. And remember, commenting on my videos is the best way to motivate me to make more. See you next time, bye!